Example 3. Do a power series substitution and then use the partial sum of the first three terms of this series to approximate the integral. So the first thing is we're going to look at the term inside the integral, and it's good to recognize that this is really just a power series in disguise. So we have embedded inside the 1 over 1 minus x, we have that x to the power 4 and it's positive, so we need to replace that with a negative x to the power 4. Okay, so that's our basic power series. So in our power series of x to the power n, we're going to replace the x with a negative x to the power 4. There's also the numerator part, so we're going to put x squared in the numerator, and since that is not part of the original power series, we're just going to put that on the outside to start. So there we've done the substitution. This expression is equivalent to this series, so we want to then simplify that series. So that series now represents the integrand of, or the function inside the integral, x squared over 1 plus x to the power 4. So we're going to set this up as a series from n equals 0 to infinity. We're going to take the negative 1 out to the power n, just to make sure that we recognize it's an alternating series. We have x to the power 4n, and then the plus 2. The 2 extra x squareds I'm going to tag on as an exponent. So that represents our function. So now that I have the function inside the integral, I'm going to integrate this and find the area. So I have the area under the curve from 0 to 0.3. Now I need to integrate that function, and by integrating the series, I will get the series that represents the integrated function. So I have the negative 1 to the power n. That's not going to be affected by the integration. I have power 4n plus 2, and then I have my dx. And I could just apply the power rule to that part of the expression. So the integral, negative 1 to the power n, doesn't get affected. The x to 4n plus 2, I'm going to apply power rule, so I get x 4n plus 3, and then I'm going to divide by 4n plus 3, which is a power, and then I'm going to apply my bounds from 0 to 3. Okay, and that represents, this is a series. I'm integrating a series, so I end up with a series as well. Move that over a bit. So that area is equal to this series now. So the area function is going to be calculated by this series. Now the question says to use the first three terms, so partial sum of the first three terms. So I'm going to plug in my n for the first three terms. So the area is equal to, I'm going to plug in 0, so I get negative 1 to the power 0, so it's positive. I get x to the power 3 over 3. Plug 1 in for n, I get negative 1. X to the power 4 times 1 plus 3 is 7. And then that's all over 7. My next term will be positive since it's alternating. I plug in n equals 2. So n equals 2, I'm going to end up with x to the power 11 over 11 minus dot, 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 dot. Okay, so I can keep on going, but this problem only asking me for the first three terms of this series, of the first three partial sums. So at this point, I'm going to plug in my bounds. So my bounds need to be here. So I have from 0 to 0.3. Now I know if I plug in 0 into this polynomial, I'm going to get 0. So I'm just going to calculate the values when I plug in 0.3 into this partial sum. So 0.3 over 3 minus x is 0.3 over 7 plus 0.3 to the power 11. Okay, and then there's a minus the 0 part of it. So if you're wondering where that 0 is coming from, it's when I plug in 0. And this part here, this is all when I plug in my 0.3. Okay, so summing that all up, my area is approximately, my partial sum of the first three terms works out to be 0.008968918. Now you don't have to really give me this many decimals, but I just want to give the decimals here to indicate how close it is to the actual sum. So that's my sum of those first three terms of the series. When I work out the actual area, and so I did this using an integral function on Desmos. So when I worked out the actual area worked out to be 0.008968917. Okay, so where it diverges is this term here. Okay, so that is 1, 2, 3, 4, 5, 6, 7, 8, 9 places, 9 decimal places of accuracy. Okay, so this is 9 digits. Okay, so we have 8 decimal places of accuracy for this function after only 3 terms. Okay, so 3 terms will give me that much accuracy. And again, if I want more, I have an infinite number of terms that I can add on to this and keep going to get a more and more accurate area estimation for that area under the curve. So again, I want you to just kind of notice that the actual area ended up being, 8 decimal places of accuracy compared to the S3, the third partial sum, the sum of the 3 partial sums gives me 8 digits of accuracy compared to the actual area calculated by Desmos.